pressure surges cause valves opening and closing, pumps starting and stopping, check valve slamming shut, air vacuum valve slamming shut, modeling for the worst case scenario, power failure. We've been talking about surge vessels. What's another way we can give energy to change in velocity of, say, a pump? Case and example is before Katrina, we had a skyscraper. Pump had been in there for 40 years, pump water to the top of the skyscraper, all is well. After Katrina, they're like, all right, we're going to go back in. FEMA's like, we'll replace the exact same pump. Not making any changes, we'll pay for the same pump. So, look at the pump manufacturer, order the same pump, put that pump in, start the pump, turn off the pump, the whole building goes, all right? Why is that? Well, the old pump, if the metal and the weight is, this much, if we make it more, let's have a good safety factor. We get into manufacturing, saving costs, minimizing material. Well, instead of have a big pump with lots of inertia, we now have a lightweight pump with no inertia. So when we turned off the old pump, it would spin slowly down and keep giving energy to the system. The new pump would stop. And a negative wave would go out and a high pressure wave come back and rock and roll the whole building. The other advantage would be to put in like a flywheel to keep the motor running. Then you've got energy costs of moving that flywheel, balancing, calibrating. I will say I did get to go to Honolulu because something happened to one of their flywheels. They took it out of service. They turned on a pump, turned off the pump, and dumped like 40,000 gallons of sewage into Pearl Harbor. And they're like, what happened? I'm like, oh, I can come to Hawaii and tell you what happened. And again, when that happens, you'll see here's a nice gate valve just ripped apart. There's there's nothing left to, that surge hit it and blew the end of it out. So you're looking at cavitation on the impeller and then cavitation in the pipeline itself. And again, you see the wear on the impeller itself from cavitation. And these are some of my favorite pictures. I got, a week ago, I got some even better pictures of impellers that were cavitating for a couple different reasons. One was they didn't have enough net positive suction head. And then the other case, they had such a huge velocity and the check valve would fail. So when they turned off the pump, it would go to cavitation and come back and just was splintering the pump itself. But just a little wear and tear on the impeller there from cavitation. What does it do to the pipes? Well, we showed some videos of it imploding and the stress in the piping separating in the cavitation. Here's some nice pipe cracks. The picture I showed you earlier, and then shredded steel pipe as you're getting that collapse. This one I think was in New York City, 42-inch line, collapsed the steel pipe. That video we've already seen. Some modeling data. Here's our flywheel. Increasing the inertia of the pump with the flywheel. Can't be used in submersible pumps where, a lot of sewage lift station using vertical turbine pumps. So it's not a solution, which is again why we turn to giving energy with a bladder vessel. Vacuum breakers, again, negative wave going out. They take time to open, which means you're subjecting your piping system to that vacuum condition. Surge anticipating valves, it's reacting to that high pressure wave. So if your negative wave going out isn't below atmospheric pressure, but the high pressure wave oscillating back is high, then we'll have a safety relief valve, a surge anticipating valve that'll relieve that high pressure wave, similar to what I showed you in the diesel model, where we're integrating the surge vessel with the control valve or the relief valve into the system to minimize the size of the surge vessel itself. Variable frequency drives, again, are always an issue, and in other cases, customers, I hear this at least once a week, oh, we're not going to have any water hammer, we put soft starts on our pump. Okay. The soft start is there to minimize the inrush of electrical current and has nothing to do with solving the water hammer problem. And the adjustment is only seconds. So that's something that always pops up.
Doesn't change shutdown either.
No. Especially if you're looking at a change in velocity that we need to occur over 20, 30 seconds. Different types of surge vessels, standpipe, again, large volume. We have a job where we're flowing 60,000 gallons a minute, and in this case we'll have an elevated storage tank to give energy to that change in velocity. Standpipes are usually issues from a water quality standpoint because they will stratify, and if we're having issues with water quality, you can get stratification, nitrification in the tank, and water quality issue if it's in potable water. Same with the standpipe like that. If that was a drinking water system, I would never drink it. I'm sure you have some beautiful biofilms in the top of that tank and maybe a few critters living and having a good old time. Bypass check valves are part of our solution where if we are pumping out of a ground storage or elevated storage tank, do I have free energy to send in behind that negative wave? So in that case, you put in a bypass check valve. We had one customer who's like, okay, we've set aside a big pile of money for you to, model our system and put in a surge vessel. I'm like, well, let me come take a look at it and take some measurements, put all that data in the model, and I go there and I look at it, and they have this nice elevated storage tank, 70 feet tall, booster pumps into the system, and I'm like, we need a $300 check valve. Let's tie it in over here and discharge it over here. This is what it'll look like in the model. This will probably cost you $2,000. You don't need a surge vessel. They're like, no, seriously? Again, the energy they had would solve the problem that they had. So it's, again, part of the solution to the problem. Typical installation. So this is something that we've been talking about, is negative pressure rating in pipe. We would like the American Society of Civil Engineers to accept negative pressure rating in pipe and to look at vacuum conditions and what is acceptable, what is not acceptable. And looking at European and Australian standards, they're more likely to define this negative pressure wave as it occurs. So again, minus 10 psig for welded steel pipe. The issue there is if you're also using air vacuum valves, they're inefficient below a minus 6 psi. So again, if you're going to accept something going down that far, we might get back into your piping is going to start to oscillate. And why not try to minimize that transient from occurring in the first place? Concrete pipe, depending on the technology, the biggest issue is when transients occur, you destroy the internal structural webbing. When that breaks, you've opened up the piping for corrosion and it'll eventually fail. Pre-stressed concrete pipe, negative pressure of 0. It's not designed to handle a vacuum condition. PE pipe, minus 10. We have had applications in some paper mills where they've completely flattened a 36-inch line in a vacuum condition. PVC pipe, they're saying minus 3. I usually don't try to drop below -2. Ductile iron pipe -6, which is pretty well respected out there for a negative pressure rating. Again, below that, there's issues with the seals. And again, looking at a model here for potable water, comparing some of the data where we can run a model and look at the minimum pressure in the nodes. It's an endless amount of input data you can get in a model, and creating graphs and minimum pressure and age of water and evaluating a big network of pipe. From simple modeling, KY Pipe offers a 3-day class that goes through basic modeling, entering your pump curve data, pump trip data, the pipeline, intermediate nodes along the way, and solving the problem. When we look at surge vessels and different applications and what, again, the surge vessel is going to look like, this particular surge vessel is an inverted bladder design, designed for solids or wastewater type application. The pneumatic precharge is in the bladder, and then the liquid or sewage is in the vessel itself. You can see at the bottom here, right, where's my mouse? Well, right here there's a grid that keeps the bladder from actually entering into the piping system in a vacuum condition. Results in a surge analysis with and without a surge vessel, giving energy to that negative wave. Comparing, I think that was one of the questions we had during lunch, is comparing a compressor type vessel to a bladder type vessel. And the biggest issue is with the compressor vessel, you're always trying to maintain that the air pocket under pressure, which that air is also trying to dissolve back into the fluid, whereas you're capturing the precharge pressure between the bladder and the vessel wall itself. And again, all the complicated pieces and parts of starting and stopping the compressor from a maintenance standpoint, and overall costs associated with that. With regard to modeling, and their function is the same. For potable water and for clean fluid applications, we're putting the fluid in the bladder. This helps reduce the corrosion of the steel vessel, so it's not subjected to the fluid itself. Even if it's water, it's chlorinated water. After a period of 10, 15 years, having to go in there and repaint the vessel is costly. In this case, the potable water is in the bladder, and I've gone to vessels that have been in service for 20 years. Inside the vessel still looks brand new. So unlike a hydropneumatic tank where you've got a corrosion issue, and I think I've got a really cool picture in here. This shows the fluid inside the bladder, how it's entering and leaving the surge vessel, either vertical or horizontal. Again, in a sewage type, solid type application, you want it vertical. In several cases, they put horizontal bladder vessel in sewage, and then you have a sedimentation issue. And that includes in a hydropneumatic tank, where then it's trying to get that out of there is very difficult. So our recommendation is always to go to a vertical style vessel. And that's just showing how it's giving and receiving energy in the wastewater. That was the dipping tube vessel I was describing earlier. This is great for a low profile system, not a lot of elevation changes, minimum pressure, flat terrain, lift station, and there's no bladder, there's no compressor. We're using atmospheric air to charge the vessel. When we start up our pumps, the liquid level comes up the dipping tube quicker to seal off the floats. Then we'd have a stored volume of air to give energy to that pump trip. That's just showing an example of how liquid's coming in and how it functions. Potable water vessels are NSF approved to, I think, 25, 30,000 gallons. ASME, U-Stamp, National Board Registered. This is my picture of a hydropneumatic tank. This is actually down the road from where I live. It blew up. The end cap ended up through a pine tree. I had another one where it went through a brick wall, but they launched the end cap off. Again, good example of surge and corrosion and not properly welded. This is, again, a detail in manufacturing, leg design, wind, seismic versus some manufacturers just take an I-beam and weld it to the side of the vessel itself. The coating that you put on the bladder to protect it, that's a 30,000 gallon bladder vessel in Chicago. Inside, again, inside's all NSF 61 approved epoxy. This is the grid for potable water, anti-exclusion grid to keep the bladder from going back into the line. Just some different pictures. This was a raw water line that we did. We modeled, had surge vessels, surge anticipating valves, air valves, high pressure, 450 PSI operating. This was for the United States Air Force, and they went to Iraq. You're thinking, this just does not look right, okay? So, 2 years before they built this $30 million pump station, we said there's a line up above the flow meter, which is the bypass line that is used to bypass the flow meter in case they have to work on it. And that we wanted an air release valve on this line because we're going to have trapped air in there, which when we have a transient wave, it's going to go into this air and oscillate back, okay? And we were also told that, we're pumping downhill and we put a vortex unit at the end, so we're basically flat. So we shouldn't have a siphon effect, okay? So this is what happened. Running the pumps, we have a surge vessel, accepted energy, it's storing, pumps are running, all is well. We turn off the pump, negative wave goes out, surge vessel gives energy, we start to gravity flow out of the wet well, high pressure wave comes back, goes up, compresses this line and oscillates back, and it starts to oscillate back and forth between the check valve and this with pressure vacuum, pressure vacuum, pressure vacuum. So here we go. That's a 36-inch check valve, and it's starting to destroy the foundation. So negative wave went back out. Here comes the negative wave. The head pressure coming out of the wet well is greater than the line pressure. So right now, we're flowing water out of the pump as that negative wave goes down. Then you hear the high pressure wave come back, check valve is going to go closed. The pump is spinning. It's allowing flow, gravity flowing through the pump. Now it's stopping. Surge tank just opened up as the negative wave went out. So everybody's run out of the room at this point. And I'm like explaining, okay, this is what's happening and this is why. And so they're they're all, you know, bent out of shape. So I'm like, this is what I told you 2 years ago. They put the air valve in, we do the same test. Dipping tube opened up. Both air vacuum valves opened up. Level dropped to 91 from 106. Negative wave went out, dipping tube open, high pressure waves coming back. Air release valves are relieving the air. Closed. Surge vessel accepted the energy, 104. Check valve remained closed the whole time. So I had to videotape both scenarios and send it back to the engineer and say, see, I told you so. We're flowing almost 10,000 gallons per minute, and they do a flying switch or the mainline pumps trip out, okay? Now the mainline, from that point on, we're pumping 150 miles, okay, to the next pump station. So we have several pumps in service, and as they're flying between these two pumps running, they'll do a flying switch to another pump. We have some back pressure check valves moving or a pump trip. So we have this inrush of pressure. This is where this pump would be pumping and then stop. It's a turbine pump and then start again, okay? And this is one of the scenarios that happened right during the BP horizon. So we spent a lot of time making sure our recommendation was right. You know, huge before and after shot. When that pump trip would go out, you'll see we went from 6,300 PSI, dropped down, you know, within a half a second, it dropped 1,000 PSI. But that piping system could handle that. There's not a lot I can do when it gets to that pressure side of the system. But you can look at that of, you know, in water flood projects and the well formation of the damage that they're doing during those transients. Loading facility, the ability to, they had 4 truck loading racks. Worst case scenario is pump trip. Loading facility, something went wrong, someone hits the emergency stop button, everything closes. That's our worst case scenario. So what happened to our piping? Looks a lot better. Air in between the two. Again, 285 PSI rating piping, keeping the pressure below that, and there's your solution. So with regard to surge analysis, computer analysis, getting real life data, it gives you the ability to work with your customer, the engineer, identify their issues, their problems, model it so that you feel comfortable supplying your equipment and minimizing your risk in solving their problem. But then once it's in service, actually going into the field and making sure the equipment works properly is the thing that, you know, our company is pushing to verify it in the field or do field adjustments to make sure everything's calibrated and started up properly. One of the biggest issues is if you lose your pre-charge or lose that energy, you go from a perfectly great working system back to the bad system. So this is where we do, you know, tie it into your SCADA system and do monitoring to make sure it's still functioning per the design. And this is one of the last things I was talking about where we're tripping 27 pumps, 4,200 pipes in a model. Just show you how complicated a system can be. You know, this includes, you know, elevated storage tanks, and then this area is where they had, you know, transient issues. We can zoom back into where we had that surge vessel. But let's just say I'm going to group that whole model and look at that pump trip, and again, citywide power failure, what's going to happen. And this is again where we have a surge vessel in our transient monitoring equipment, and every year I go take a look at it, upload my computer, and I can tell them when they are running certain pumps, how their pumps are running, and when they did have a power failure. And the best part to me was, yes, they did have a power failure, and my model matched the real life data perfectly. So in this case, we're running, all those, there's literally millions of calculations going on and we can pick any individual node and see what the pressure envelope is on your street, or, all through the whole system. Then, because it's such a huge model, we can highlight, okay, I want to know everywhere where the pressure dropped below, say, 15 psi, to make sure I'm protecting the whole entire system. And, there's, again, endless amount of reports and data you can get. I could go on forever because there's a whole PowerPoint just on that particular model. But again, I wanted to give you a feel for the modeling, and solutions. And